This is 7-3 day 1, integration by parts. The first day we're doing very basic things, so on the homework you won't be choosing what we will come to know as U and dV. We'll actually be giving you help on how to choose those tomorrow. But backing up, we have methods for integration, in other words methods for finding antiderivatives. I'm not talking about ones that are definite integrals where you'd be going from 2 till 5, or things where we could estimate by area under the curve. We're talking about the general case. So we're looking for a function whose derivative is the value that they've given us. So we've done this before. On the first example, we've used known antiderivatives in order to find the integral. So in this case, because we know the values that could have led to 3x squared as a derivative, we know that that came from x cubed, plus we know that 5x as a derivative came from 5 half x squared. And we know that in general, if there had been a constant in that function, it would have dropped out, and therefore for the general case of what function could have had a derivative of that integral's value, we've got the general case. So be the waitress, add the constant. After we did that for a while, trying to think sort of in reverse, we discovered that U substitution was helpful. So on this one, we'd make our U 3x plus 2. So that our du, or derivative of u with respect to x, is 3 dx. Coming back to the equation then, we could substitute some things in and change some things around. We need a 3 in this in order to have our du up here, so we knew we could put a 1/3 out front to balance that, and then we could u substitute and change this into 1/3 times the integral of u to the 1/2 power du. We would then evaluate this integral, which would be 1/3 multiplied by, and then as we think about what u to the 1/2's antiderivative is, it's 2/3 u to the 3/2 plus a constant, and then switching those u's back so that we no longer have them in terms of u's, but back in terms of the x's that we were seeking a function in. So we'd have 2 9ths, and then again our function, 3x plus 2 to the 3/2 power, plus a constant is the general form of a function who's had for that integral. What we're going to do is come across ones that we can't do that way. So integration by parts takes from product rule for derivatives and moves it around to make an equation that we can use to break certain integrals into parts so that that integrand can be evaluated. So as you know from evaluating derivatives, if we come up with a function that's really a product of two other ones, then the rule, and we usually simplified it, but we need all these du's and dy's and dx's, the rule for its derivative then would be one function times the derivative of the other added to the other function times the derivative of the first. So as we work through this, we're going to take and prove or sort of derive the formula that lets us do this by parts. So as we rewrite this, the first thing I'm going to do is just rewrite y as that function u times v. In other words, derivative of the function u times v with respect to x on this side. And then this side I'm really going to leave it mostly alone for a little bit. That's sort of that product rule part. Now that I've got this rewritten in terms of u's and v's only, so no y in there anymore, I'm going to rearrange and just move some terms by addition and subtraction. So I'm going to keep this u term by itself, so that u dv dx is going to be over here by itself. And I'm going to bring then, in order to keep it over here by itself, I basically have to subtract this one on the other side. So derivative of u times v with respect to x minus v du dx. So far it's just rearranging product rule. After I rearrange product rule, then I can actually do an antiderivative. I can actually do an integral for each part of this, and we will come up with the rule that we're going to use for integration by parts. So when we do that integral, each one of these gets a dx in order to accomplish it in terms of x's, in other words, letting us know what we're using as our variable of integration. So over here they cancel. We've got the integral of u in terms of v is equal to, we have on this side the integral of a derivative. D of u times v dx is a derivative, and we're taking its integral. So those will cancel, and the derivative of this, and then we integrate it, is just u times v, in other words, undo and redo, minus v's derivative in terms of u. And this whole thing, deriving from product rule, becomes what we're going to use for integration by parts. And it seems a little overwhelming at first because you're seeing the derivation of it first, but it's a formula that we'll keep using and it will start to feel more comfortable. So how do we use it? Just some basic examples because that's all you're doing on the first day. To do this, we want to be able to break whatever function they've given us into two parts. We want to be able to break it into a u function and a separate dv expression. And at first we're going to help you by telling you what to use for those. So we're going to break this integrand, all of this, into a u function and a dv function. So helping you out the first day to pick your u's and your dv's, I'm going to break it up like this. In the next couple days we're going to spend a lot of time deciding how we pick those so that we can have success with this method. This method doesn't work every single time, but we want to up our chances of finding functions that will be able to be integrated this way when substitution and just direct antiderivatives doesn't work. So then what I need is I need to know what the derivative of u is. So in other words, on this one we're going to take a derivative, which would be 1 times our differential in terms of x. And on this side, we need to do an antiderivative. We know the derivative of the v function. We need the v function back. So we're saying whose derivative is cosine, and that would be sine. Then we're going to take all those pieces we just found and put them into that formula that says, okay, if you want the integral of this function, x cosine x dx, you need to do the u times the v. So x sine x, take away the integral of v sine of x, du, which in our case is just a dx. So everything got subbed from up here into that formula, and now we're going to evaluate. So this first part, x sine x, is already done, minus the integral of sine x in terms of x. Well, the integral of sine x is the opposite of cosine of x plus a constant. So our general case for this one then, our general integral is x sine x plus cosine x plus a constant. So we have that function whose derivative then is x cosine x. Now to check, because this seems like a little bit of voodoo at first, and we won't do this every time, but let's check this with derivatives. Let's see if we take its derivative. So we're just doing a check here. This is not normally part of the process, but to sort of believe it the first time, we're going to do a derivative. A derivative of that function with respect to x, and let's just make sure that we see that it works. So the derivative of x sine x, I would have to come by product rule, so that would be derivative of the first times the second, plus derivative of the second times the entire first function, so that takes care of derivative for that term, plus derivative of cosine is the opposite of sine, or negative sine of x, and then derivative of that constant would be a 0. So as we look through this expression, the sine terms will cancel themselves out, and we're just left with cosine of x times x, which was our original function, so we do have an antiderivative to that function. Last one. So as we go through, we see a function and we don't know its integral. Okay, we don't know its antiderivative. And you'd say, sure, 1 over x. Well, 1 over x is natural log's derivative, not its integral. So we're going to pick, like we said today, we will pick for you, even on homework, and then we'll work on how to pick those u's and dv's as we go. So in this case, I'm going to let that natural log function of x be my u, and just that dx, or a 1 dx if you'd like, to be my dv. So first things first, I need to find something, I need to find u's derivative. So u's derivative is 1 over x dx. V's antiderivative, or integral value then, is x. So we go through and put those into that formula, and that formula is up in the upper left-hand corner if you need to see it, so that we can find out the integral of the natural log of x. Here's what we're going to come up with, the u times the v. So x natural log of x minus, part of the formula, the integral of v, and then we need to put that du expression in there. That's where we're going to pick up our differential, by the way. So that first part's already worked out. Minus, really these x's cancel each other out, so I'm really doing the integral of the constant 1, which would just be x, plus a constant. So on the assignment, as you're doing the assignment, really when you look on the worksheet, it's broken into 3 parts and you're doing a lot of matching. So as you look on the worksheet, and you see that at first in the directions it says, and the directions are in the middle of the page. So for number 1 it says match each integral with a u and a v. So you go down to the boxes and you're going to write down the letter A through W. Once you've matched it to the u and the v that should work, then you're going to go down to the bottom boxes and match it for an integral setup that should work. If you have letter C, or if you have, for letter C, if you have an asterisk, you need to actually go all the way to getting the antiderivative value or the integral for that particular function. By the way, keys are in classrooms.